Oh, how many of you are taking physics 2 in the summer? Okay. Okay, it's a 6-week course, you know, 2.5 hours of lecture every day. Okay. All right. So, in the first part of this chapter, you studied the following. You had an object like this. You had an extended object, and several forces would act on this object. And what is it that you wanted? You wanted this object to be at rest. Okay? So when several forces act on this object, on an extended object, you need two conditions for static equilibrium. And the two conditions that were necessary for the object to be at rest was the sum of the forces needed to add up to 0. Okay? And the sum of the torques of these forces needed to add up to 0. Okay? So those were the two conditions for static equilibrium. Okay? So for instance, on this object, let's say if you were climbing up on this ladder and you didn't want this ladder to move, here are the various forces acting on this object, and this was done by drawing the free body diagram. What does the free body diagram do? It shows you all the forces acting on the object and where the forces were acting. Okay, so for instance, this wall, this is assumed to be a smooth wall, applies a normal force on the ladder, and that's that force. The ground, the floor applies a normal force. There's a normal force, and in addition, there's a friction force. What kind of friction is this?
Static friction.
Static friction force, very good. Static friction force. This is the weight of the object acting at the center of gravity of the object. And the center of gravity of the object, for this object, since this is a small uniform object, happens to be at the geometric center. Okay? And if you were climbing, there's your weight. So 1, 2, 3, 4, 5 forces acting on this object. And for this object to be at rest, the sum of these forces need to be 0, and the sum of the torques of these forces need to be 0. Okay. Now, let me ask you this. As you climb up the ladder, will any of these forces change?
The friction force will change.
Very good. Very good. Okay. So, as the application of the forces change, some of the forces might change, but you don't want that ladder slipping no matter what. Okay? All right. All right, so that was the first part of the chapter. Now we'll look at the second part of the chapter. Okay, so this is sort of seems like an unrelated topic. It is a very different topic, but it's useful in when you do construction and all that kind of stuff, where you'll be dealing with static equilibrium. All right, so here's an object. We'll apply two different kinds of forces on it. What is this force doing? So let's say you have an object and you hold on to it, grab onto it from either end and pull. This is what is called a tensile stress. Okay, so you're trying to elongate it. Okay? And here's the same object. You're applying the same forces, except that now you're compressing it. Yeah. All right. So let's say we apply the same force. This is 1,000 pounds, 1,000 pounds, 1,000 pounds, 1,000 pounds. Okay. Do you think this object would break first in either case? Or will it be equally strong for both kinds of forces? So this is tensile forces, this is compressive forces.
It depends.
Okay. So if you were to guess.
It would break under tensile first, generally.
Yes, so generally its objects are stronger under compressive forces. Okay. So let me show you a table. Okay, so concrete, this is the compressive and tensile strength. The strength meaning what kind of forces will break it. Look at this, concrete is 10 times stronger under compressive forces. Cast iron is 3 times stronger. Okay? Your bones are 50% stronger under compressive forces. Okay? So here's the deal. As soon as you look at this table, if you're a civil engineer, what you're thinking is, if I'm going to apply large forces, I'm going to make sure that they're compressive forces. Okay? Okay, so that's what we want to study. So for instance, this bridge, a suspension bridge, if it's to support, let's say, 1,000,000 pounds, what is happening is essentially this guy is supporting 500,000 pounds, this guy is supporting 500,000 pounds. And all these structures, what they're about is the 500,000 pound is pressing down. It's a compressive force. Okay? That's the design of the bridge. Okay. All right, so here's what's happening. I don't know, we might have talked about this briefly before. Did we talk about this?
Each
Okay.
string holds up a portion.
Yeah, that string, all these strings are adding up 1,000,000 pounds, but those are all tensile forces. These strings are being pulled and they effectively pull this guy down, and that is applying the compressive force. Okay. All right, so again, where did all that start from? Where did all that analysis start from? When somebody looked at a table like this, you realize that structures are much more stronger under compressive forces than tensile forces. All right, so so that's what we're going to look at. All right, now we'll try and understand this bullet point. Internal forces that arise because of deformation balance the external forces. Okay, what we are trying to understand is the following. Okay, so let's say we apply a tensile force to this. You can apply the same argument to the compressive forces. When you apply tensile forces, this deform, this stretched a little, any material, concrete, your bone, a piece of wood, this stretched a little. Okay, so let's go to this example. Here's a metal that's clamped down. I apply a 100-pound force and it stretches this much. And generally, this happens if you apply a 200-pound force, it stretches how much? How much?
Twice as much.
Twice as much. How did it know how much to stretch? And then why did it stop?
It stopped because the internal forces match the amount of applied force.
Okay, so here's what happened. Okay, so when you stretched it, you can think of all these atoms, the forces between the atoms modeled as springs. Okay, and when you stretch it, you're stretching each of those springs. Okay, so let's say, as our friend here just said, let's say I applied 200-pound force. Okay, each of these guys stretches such that all these forces add up to 200 pounds, and then it stops stretching. Okay, so it stretches enough such that all these internal forces add up to this external force. Yeah, and that's when it stops. All right, so that's what's going on. All right, so in this chapter, we'll consider 3 kinds of deformations. Okay, you saw when the length changes. Okay, so one of the kinds of stress we're going to apply is we're going to apply forces like this, and the predominant dimension of this object is the length, and the length changes the most. Okay, when you pull on this object, the length will increase. Does the cross-sectional area change?
Yes,
And what will happen to it?
it'll shrink.
It'll shrink. Okay, but it'll shrink less, and so we won't worry about that as much. Okay, the other deformation we'll consider is the volume deformation. Okay, so we'll apply this kind of stress. We'll apply perpendicular forces to the object, and its volume would decrease. When would this happen? Can you think of a situation when this would happen?
Like a sponge?
Yeah. So if you put an object underwater, there's pressure on it from all sides, okay, and the pressure is perpendicular and it'll shrink. Okay. The other deformation we'll consider is the following. we'll apply forces like this on opposite sides of the face, okay? And then this layer will slide with respect to that layer. Okay? And it happens when you are when you're using your scissors, for instance, okay? Then on this layer of atoms, you're applying a force in that direction, and this layer of atoms, you're applying a force in this direction. And the two layers, well, you'll get a cleavage there, okay? And they'll slide, and that's how you're cutting. And that thing cleaves. Okay, so those are the three deformations we'll consider. You're changing the length, you're changing the volume, and you're sliding layers against each other. Okay. All right, what we want to consider is elastic behavior. Okay, so what we want is we'll apply a stress, and when we remove the stress, what happens?
It returns to its original condition.
Yeah, it returns to its original condition. All those, so going back to this this example, you apply a stress, you remove the stress, and all the springs will go back to their original shape. Okay? And now when we want to use these materials in our constructions and stuff like that, you want this elastic behavior to be exhibited how many times?
Forever.
Forever. Okay? All right, so that's what we're looking at. Okay. All right, so that's the point of this section. Okay, so we're going to apply stresses. Object will deform. The deformation is measured in something called strain. The object is strained. Okay? And we'll define elastic moduli. Okay, so when an object is in either tension or compression, the object deforms by changing its length. Okay. All right, so we are going to stress this object. Okay. So here are the two terms that are relevant in this chapter. Stress is defined as force per unit area. This force that you applied per unit area is the area of cross section. Okay? And the other term is strain. Strain measures the deformation, or how much the object got deformed. And strain is defined as change in length divided by, in this case, it's defined as the change in length, that was the relevant dimension that changed, divided by the original length. Okay. So under this stress, this object underwent that much strain. Okay. All right. So again, here are compressive and tensile strengths. So as you can see, tensile strength for most, tensile strength tells you under tensile stresses, when does the object break, okay? So tensile strength for the objects is always less than the compressive strength, okay? Marble is different marble have different properties, so depending on the crystal structure, that's why, so you can't uniformly measure that. Wood is one of the few objects where it's more stronger under tensile stress. Yeah. All right, so let's say this is just a rhetorical question. So here's a bar, and when you're lifting the bar, it bends like that, and so the top portion is under tensile stress, and the bottom portion is under compressive stress. So if at all the bar were to crack, that's where the cracks would develop. Right? You guys understand? Okay. All right, so here is volume stress or bulk stress. Stress is equal to the external force acting on the object per unit area. So again, and strain is the measure of degree of deformation. So we defined properties called elastic moduli. Elastic moduli. So we'll consider three different types of stresses. So we'll define three different elastic moduli. But elastic moduli is stress over strain. So for those three different cases. And again, what are the three different stresses we are considering? On objects where length is the predominant dimension, we're considering tensile stresses and then volume stresses, and the third kind of stress we're considering is shearing stresses. Okay? These are all forces. Okay. So we'll define elastic moduli for these three types of deformations. Yeah.
Why is compression not included in that
In what?
for or compressive stress? Or is it just included in volume?
For this guy?
Yeah.
Well, it's for small deformations, it behaves the same way. The elastic behavior is the same. You can apply the, so if, let's say you take an aluminum rod, apply a 500-pound force and it stretches 1 millimeter. If it's compressive, it'll compress 1 millimeter. It's just stronger. The upper limit is higher. Similarly for this guy, so for the volume, if you're applying compressive volume, the volume decreases, but let's say you apply a stretching stress, so you put it in vacuum or something like that. Yeah. All right, so Young's modulus measures the resistance of a solid to a change in its length. Shear modulus measures the resistance to deformation of parallel planes within the solid relative to each other. So this is shearing stresses. Okay. And shear modulus, higher the shear modulus, harder it is to strain it like that. Okay. Higher the Young's modulus, harder it is to stretch an object. Okay. That's what the elastic moduli tell you. And greater the bulk modulus, harder it is to compress an object. Okay? So that's what those moduli tell you. So Young's modulus is denoted by Y, okay? And that measures the tensile stresses. So Y is, the Young's modulus is tensile stress. Again, all moduli are stress over strain. Young's modulus is tensile stress over tensile strain. The stress is force divided by the area of cross section. Strain is the stretch divided by the original length. So this is the percentage deformation. Okay. So if a 1 meter's rod stretches 1 centimeter, that's a 1% deformation. Okay. And of course, 1% deformation is kind of hard. Okay. We'll do numbers in a second. Okay. This is dimensionless, the denominator, and the numerator is Newton per meter square. Okay, so the units are Newton per meter square, the same units as pressure. Okay, but we don't call it pascals here because it's in a different context. Okay, so when you're talking about pressure, we call this combination pascals. Okay, but here we don't. So all right, so keep in mind these cables on the bridge. Okay, so we're talking about this. Okay, so those cables, yep. Mm-hmm.
Is Pascal the same as PSI, or is that something different?
PSI is pounds per square inch. Yeah. Pascals is the SI unit. Yeah.
In terms of their equivalent, essentially.
Yeah, dimensionally they're the same. Yeah, they're different. All right, so now we'll keep in mind those cables on the bridge, okay? All right, so you have loads applied, so a whole bunch of, and this is supporting, so you're applying tensile stresses and the cables are stretching, okay? You apply this much stress, the cable stretched this much, okay? And then when the stress goes away, the cable goes back to its original length, okay? what this is, as long as the stress is less than that, you are in what is called the elastic limit. Okay, meaning you double the stress, the strain doubles, okay? And if you're within the elastic limit, when you remove the stress, the cable goes back to the original shape, okay? And that's what you want. Okay. If you apply a stress beyond this point, this is, permanently deforms. And the cable won't go back to its original shape. Okay? And this is the yield point. Stress is greater than that, the the cable will crack or whatever. Okay? And again, this behavior is, it's not always reproducible, but and this is fractured. Okay, so if you're building any of structure, you want to be well within the elastic limit. Okay. So, how do you decide how many cables you're going to put on that bridge? So, how would you decide how many cables you're going to put on that bridge?
You would divide the capability of each cable with the total mass you expect divided by how much each cable can lift.
Yeah, so you imagine the worst case scenario. The worst case scenario is pack this thing bumper to bumper with semis, loaded semis. Okay. And then do a calculation where even with loaded semis, you don't go past that kind of stress. Okay. And then you're good. Okay. If you put too many cables, of course, the bridge is going to cost more. But but that's the kind of stuff. So you're balancing safety and cost. All right. So now we'll look at shear modulus. You're going to look at shearing stresses. What you're doing is applying forces parallel to the faces in opposite direction, and it's deforming this face is moving relative to that face. Okay, so that's the shearing stress. Okay, and the way to measure shearing strain is how much did this top layer move relative to the bottom layer. Okay, and how far apart they are. So the strain is measured as delta x divided by h, the distance between the planes. Okay. And again, this is dimensionless. And stress is the force you apply divided by the area of the face. Okay. Again, units are Newton per meter square. And okay. So smaller the deformation, smaller delta x is, greater S will be the shear modulus, stiffer the material. Okay. So for instance, you take a steel block and a wood block, the shear modulus for steel would be much higher. Shear block versus aluminum block, which one would have a higher shear modulus?
Steel.
Steel, yeah, so easy. Okay. Here's bulk modulus. In bulk modulus, you're changing the volume. Okay, so the stresses you're applying are forces perpendicular to the face, and most of the time we're applying forces such that the volume decreases. Okay. Okay, so the stress is force divided by the area, I guess. So, and again, the forces have to be equal in all faces. Otherwise, what will happen if the forces are not equal?
It'll just move.
Yeah, it'll just move. Yeah. All right, so you want to apply equal forces. So this is stress divided by the strain. The strain is change in volume divided by V. What is this minus sign doing here? The volume is shrinking. The change in volume is negative. Negative times negative will make it positive. Okay? So there is the bulk modulus. Okay. All right, so all these moduli are important enough where people make tables, they go measure it, so a material science engineer will go measure this. And here are these numbers, and that engineer who designed that suspension bridge is using these tables. Okay. All right, let's look at what these numbers mean. Okay, so I'll do just an example. Let's take a steel cable. So where is steel? Okay, the Young's modulus for a steel is 20 times 10 to the 10 pascals. Okay, so what we're going to do is we're going to take a steel cable, and its area will take a square cable just and 1 centimeter on the side. 1 centimeter, so it's a cable that thick. We'll take it 1 meter long. Okay, you guys have seen a meter stick in the lab, so you can take 2 meter sticks and put them together, and that would be something like that dimension, 1 centimeter by 1 centimeter. And let's put a load on it, okay, and see what kind of load would you have to put such that it stretches 1 centimeter. Okay, so it deforms by 1%. You guys understand what I'm doing? So this is force divided by area, delta L by L. Okay. Force is, we are going to hang that, and 1 centimeter square. Area is 1 centimeter square. 1 centimeter square. 1 centimeter by 100 centimeters. So mg is y times 1 centimeter. Okay. So y times, this is 0.01, and this is, that's 10 to the minus 2 meters, so that's 10 to the minus 4 meters squared. So the Young's modulus is 20 times 10 to the 10 pascals, Newton per meter square, times 10 to the minus 6 meters squared. And that's 645 newtons. Well, that is, divide that by 10, that's 20,000 kgs. So if you take a steel rod about that big, 1 meter long, you would have to hang 20,000 kgs with just 20 small cars, and the cable would deform 1%. That's what that number means. Okay? All right, so obviously that's the kind of calculation you would do on those cables that you use in suspension bridges and stuff like that. Yeah. All right, so here you saw this table, okay, and this is where your decisions start. Okay, so concrete is, this is the tensile strength, and this is the compressive strength. Okay, it's stronger under compression, and you put tensile stresses on it, and it doesn't like it. Okay, you develop fractures. So let's say you build a bridge like this. Every time a car goes by, the bridge buckles, and the underside is undergoing tensile stresses, and the top surface is experiencing compressive stresses. And you learn this through experience. Over time, you develop cracks at the bottom of the bridge. And so you want to fix that problem. So here's what you do. You put reinforcing steel rods, but again, you would still experience cracks. So here's what eventually we have come up with a solution. So what you do is you take these steel rods, reinforcing rod, and when you're pouring the concrete, you stretch them. They're under tension. pour the concrete, let the concrete cure, and then let go of the tension. Why did you do that? Okay, so now when you let go of the tension, the steel rod is compressing, it's putting that concrete under compression, compressive forces. And then you put them on the bridge. And now when a car goes by, when this stretches, the bottom stretches, it's only going back to its original shape. Okay? So this is pre-stressed concrete. Okay? And that structure will last longer. Okay? So you see, you looked at this table. You looked at this table and you instantly got that idea. That's how you became a good engineer. All right? All right, guys, so that covers this chapter. I don't know if they still use these things, what these are. This was a device, if you design a structure like this measures via optical activity where the structure has greatest stress, okay? What they do is, I don't know if these guys still do them. So you have two polarizers, you'll build a model of the structure. So let's say a model made out of transparent material, plastics or something like that. And on top of the structure, you put a weight. And so which joint is the weakest, okay? So now what you do is you send polarized light. And the plastic, depending on the stress, it turns the plane of polarization. Okay? And so that's one way to measure practically which joints are bearing the most stresses. And then once you find that information, what do?
You reinforce those areas.
There you go. You slap more cement there. Okay? All right.